Welcome to Science Goes to the Movies, a look at the stories of science and how they change our culture. I'm Lisa Beth Kovetz, and I've got questions about Star Trek's newest franchise, Strange New Worlds. And one of the best things about shooting the show at the City University of New York is a pretty near guarantee that one of our professors will be able to answer them. And so, I am delighted to have astrophysicist Emily Rice of CUNY Macaulay Honors College in the studio to talk about Season 1, Episode 4 of Strange New Worlds and what that episode has to say about her specialty, brown dwarfs. Emily, welcome to the show.
Thanks for having me. It's so great to be back.
Delivering supplies to a distant outpost, the Enterprise is unable to make contact with the planet below. Mr. Spock suggests that a large brown dwarf in the vicinity is causing radio interference, jamming the signal. First off, what the heck is a large brown dwarf?
A large brown dwarf is technically a star, but so a brown dwarf is this astronomical object that we think formed like a star does, so from a collapsing cloud of gas and dust, but it never got enough mass to have a high enough temperature at the core to fuse hydrogen into helium and shine like a star. And so sometimes they're called failed stars, which I don't really like because I like to think that my objects are successful at doing what they want to do. And so if you have too much mass, a brown dwarf could become a star, but the brown dwarfs themselves are these kind of lower mass objects.
So they are doing the nuclear fusion that a star does, or they're not?
They do a little bit. So that's the thing, is that they do a little bit, but they never stably fuse hydrogen into helium. And so there's a big difference between the things that can fuse the hydrogen. It kicks off. It's like kind of think of it like an engine turning over. So sometimes, a brown dwarf, like the engine will turn over a little bit. It'll fuse lithium, it'll fuse deuterium, which is heavy hydrogen, but it fuses at a lower energy. But neither of those things are very abundant. You don't get a lot of energy out. Whereas when the hydrogen fusion kicks in, that's just works. And
star.
Yeah, immediately. And a low mass star is super cool because, well, it's literally cool, but also fascinating because it will last for a really long time. So it's this tiny little engine, but it kind of fuses at such a slow rate that it'll last longer than the universe has been around.
Oh, interesting.
Yeah.
Interesting. Slow burn lasts forever.
Yeah. The stars are like the massive stars are like kind of live fast, die young type things, but the low mass stars and even the brown dwarfs are basically going to stick around forever.
Live fast? How fast? It's still billions of years.
For a massive star, it can be millions of years, which still, I mean, still. A million years in astronomy is, we throw them around.
In the episode, they're having radio interference. Is that a legitimate thing? Would a brown dwarf cause radio interference?
Yeah, that's really the cool thing. Like this one, they got it right. And so we have aurora on Earth that are caused by the charged particles from the solar wind kind of getting accelerated in the magnetic fields of the Earth. And so it was an open question for a while, like would the brown dwarfs have this auroral activity and like the Earth? And it turns out the answer is yes. Like we've been observing these aurorae in radio wavelengths for several years now, and even more recently in visible and infrared wavelengths, which is really, really cool.
And those things cause radio interference?
Yeah, it totally can. So it's kind of a radio wave is a radio wave. And so this is why if maybe you go on a tour of a radio telescope and you don't get a cell signal there, because those are all radio waves. There's a really interesting astronomy result a while ago that they were like, where is the signal coming from at this radio telescope? And it turned out it was interference from the microwave in the staff cafeteria. And so you really have to be careful. Like the radio waves that are coming from space are the same radio waves that we use for communication on Earth. And so it's just, it's the same reason that your kid's walkie-talkie picks up the police scanner sometimes, because those frequencies that we use for this communication overlap.
That's fascinating. And what attracted you to the study of the brown dwarf?
That's a really good question. I've basically studied brown dwarfs my entire career. I think it was because they were new at the time. So when I started graduate school about 20 years ago, both the brown dwarfs and the exoplanets were very, very new. Weirdly enough, they were both discovered in around the mid-1990s. But exoplanets was a really hot field, really, really competitive. And the brown dwarfs, nobody really cared about them as much. And so I got to work on these kind of underdog things. And so there was still a lot to be discovered and a lot to learn about them, but it wasn't as competitive and cutthroat as the exoplanets were.
So let me just unpack that just a little bit. How does something as ancient and long-lived as a brown dwarf What do you mean it was new? How does that become a new thing, something so old?
Yeah, so these brown dwarfs are really, really hard to find because they're so low mass, so cool that they don't emit a lot of light at optical wavelengths, at visible wavelengths of light. And they were kind of postulated to exist in the 1960s. So astronomers in the 1960s started to work out, okay, we know that there's stars of different masses, and we can start to measure these different masses and figure out how the stars are different. But what about the lower mass ones? They get smaller, they get dimmer, and so they're harder to find with our current technologies. And somebody said, okay, what happens if a star is actually not massive enough to fuse hydrogen into helium? Like, we didn't know if the universe could create these things, and it turns out the universe does. And in fact, there's more of the smaller things created than the larger things. But it took our technology 30 years or more to catch up to be able to observe really the entire sky at infrared wavelengths of light. So the longer wavelengths of light is where these objects are actually a lot brighter for us to see.
Was it an issue of math said maybe and then technology confirmed?
Yeah, yeah. And it was also a little bit of like, how are the objects going to work? So what wavelengths of infrared light to look for and things like that, but for technology to catch up. And sometimes to be declassified a little bit because a lot of our space technologies come from the defense industry.
Oh, very interesting.
Yeah.
And do these celestial objects have any impact on us here on Earth?
You know what? Only for the astronomers sometimes, I think. Like, I joke about that with astrology sometimes.
It impacts you.
Yeah, it affects us more than anything else. For the brown dwarfs, like, sometimes. So every once in a while, there's this rumor goes around about Nibiru or something in the outer edge of the solar system. There's always rumors that there could be something out there disrupting the Oort cloud or the Kuiper belt of objects, and people are like, astronomers are actually looking for it. But we now that we've had some infrared all-sky surveys that have been pretty sensitive, we think it's less and less likely that there's something really massive hanging out around there. There might still be like a 10 Earth mass planet or something that people are still looking for, but we don't think that there's like a rogue brown dwarf, for example, between us and the nearest star.
That's so Star Trek, a rogue brown dwarf. The newest big bad on Star Trek is the Gorn, and to escape their murderous attack, Captain Pike instructs the crew to fly directly into the brown dwarf, and you can tell, by the way Mr. Spock just barely raises his eyebrow, that he thinks it's terribly dangerous. But could a spaceship actually maneuver inside this brown dwarf?
I think so, yeah. Like, this is a little bit weird because eventually they start to talk about like the dust cloud kind of around the brown dwarf, and they start to talk about an accretion disk, which is a real thing. But at first they don't mention that, and so I wasn't actually sure, are they going into the brown dwarf? But I think they did. And a brown dwarf is, I mean, it's definitely safer to fly into a brown dwarf than to fly into the sun, definitely. And it's just a cloud. Like that at the beginning of the episode, they say, oh, it's basically a gas giant, which is a little bit dismissive. But yeah, it's like flying through a cloud, especially at the upper layers.
The young Mr. Spock tells Captain Pike that the center of the brown dwarf has a mass that will crush the ship. And I thought, I got to check that with Professor Rice. So will the mass increase as you get closer to the center?
Not quite the mass, but the density and the pressure are going to increase as you go in. And so this is definitely something like they're going to want to maneuver very carefully because the upper layers might be okay. But the deeper in they go, it's going to get hotter, it's going to get higher pressure, it's going to get a higher density, and that's definitely going to be a little bit more dangerous.
Okay, so because I know nothing about anything, when we say the mass increases, are we talking about the mass of the brown dwarf increases or the pressure on the ship increases because of gravity?
Yeah, it's the pressure on the ship that's increasing because of gravity. Yeah, because the mass is there. And really for the pressure and the density, we really only care about the mass that's inside of where the ship is. And the ship is getting closer to the center, so there's actually less and less mass inside. But there's also less volume. And the volume that's important for the density and the pressure goes as r cubed. I did some math, but it's not too bad. So the density increases. It's similar to how atmospheric pressure on the Earth, and you go higher and higher up, and there's less and less atmospheric pressure. And so for the brown dwarf, it would be very, very similar, where lower down, closer in towards the center, there's going to be a higher and higher atmospheric pressure. But with the Earth, our atmosphere is like very, very thin. It's like the skin of an apple on this solid rock. And for a brown dwarf, much more similar to Jupiter, it's basically atmosphere almost all the way down.
Right. So what the Enterprise is experiencing is being crushed.
Yeah. I like this episode because it's much more analogous to like a submarine. And they talk about diving, and they talk about the torpedoes, and it becomes much more about a ship. And the ship really does function like a submarine in this episode.
The Enterprise is in the brown dwarf for about 17 minutes of TV time when the ionic gases of the cloud begin overwhelming climate control. And it's getting hot on the Enterprise, but I thought space was cold. Why would it get hot?
The inside of the brown dwarf is going to be hot. And so even though these brown dwarfs are failed stars, like they don't generate their own energy from the core via nuclear fusion, they do have a lot of their own energy. Like they have a high temperature that's left over from their initial collapse. And so these brown dwarfs are kind of like embers that are in a fire that's gone out, but it's still warm in there. And they just cool off so slowly that there is still a lot of heat inside. And so as you go deeper, it is gonna get hotter and hotter inside of the object.
Does the temperature affect the color of the?
Yeah. Very similar to the stars, like the hotter stars are blue and the cooler stars are red. The brown dwarfs are also gonna have different kind of visible properties or optical properties depending on their temperatures. But for the brown dwarfs, it gets even more complicated. So it's temperature, it's also the composition of the atmosphere, where you're looking and things like that. And so we usually kind of picture the brown dwarfs as magenta or dark purple or something like that to kind of represent that they're brighter at these longer wavelengths of light.
It just occurred to me that we talk about them being cooler than suns, but they still must be astonishingly hot if they're cooling in space over long periods of time.
Yeah, they can still be thousands of degrees. Yeah, they start out thousands of degrees and then cool off over time. And it's really hard to find the even cooler ones.
So they started to generate heat the way a sun did, but then they didn't get enough matter?
They didn't have enough matter overall, like to push down and create a high enough temperature and density at the very, very core. Because in order to like smash those atoms together to get nuclear fusion starting, you have to have a high temperature, something like 1,000,000 degrees.
I never really thought about, I know you don't like to call them failed stars, but failed stars, and how lucky, how unique, how rare it is that we do have this working star and this solar system and an atmosphere. It really is an extraordinary thing.
Yeah, we're like in our exploration of space, we're trying to find all these stars, we're trying to find all these planets, and it's fascinating to me because throughout history, some of the things we've learned is that we're not unique. We're not the center of the galaxy, we're not the center first we're not the center of the solar system, then we're not the center of the galaxy, and now our question is how unique is the solar system? And partially, we're not sensitive to exactly the planets in the order that we have in the solar system, but at the same time, so far, our solar system is kind of unique. Like there's lots more possibilities out there than we ever could have imagined. And so it's a really fun time to explore planets around other stars.
In the middle of the episode, no surprise, the drama really heats up. Captain Pike asks for the status of the ship's torpedoes, but Mr. Spock warns him that inside the brown dwarf, the weapons guidance system will fail and the torpedo will fire in a random direction. Is that a science-based reality or fabulous technobabble?
I think that sounds like technobabble to me a little bit. Maybe the idea is that because they're inside the brown dwarf and it's opaque, like it's optically thick so they can't see anywhere. I think that was the big idea of the episode, is that they're inside this thing, and so it's basically like inside of a cloud. And so we can't see, but like at the same time, they could use a longer wavelength of light. Like there are things that they could use to maneuver and to navigate. But I guess with the photon torpedoes, they're at such a wavelength where they're going to get confused as well, it sounds like.
Their guidance system wouldn't have anything to bounce off or to triangulate.
It would the opposite actually is that it wouldn't penetrate through the atmosphere. And so it would bounce off so much that it would get confused.
Oh.
Yeah. Yeah.
It's that density that we were talking about.
Yeah, it's the high density, and there's just so much there. So the refractory elements, the volatile elements, everything's in there. And so the photons are all bouncing around, and they don't escape, and they don't travel freely.
Brown dwarfs are kind of cool. The brown dwarf in this episode is tethered in orbit around a black hole, which sounds exciting and ups the danger, but is that possible? Could a brown dwarf be tethered to a black hole?
Yeah, they could definitely be in orbit around one another. This is a funny part to me because like the brown dwarf is actually so much harder to find than the black hole. And so they're focused on the brown dwarf, and then it's like, okay, the black hole was actually here the whole time. Like, and that hasn't come up before. Yeah. And it's maybe surprising. It depends on the mass of the black hole and things like that. But we now know that like basically anything in space can orbit anything else. And there's different ways that these binaries could have formed and things like that.
And is that what they mean when they say tethered?
Yeah.
So
yeah. They're orbiting one another. Yeah. So they're gravitationally bound. Yeah. They're tethered to one another by gravity, really.
Interesting. Back on the Enterprise, Erica, the helmsman, asks how big of a black hole. Does size matter with the black hole?
Yes, absolutely. Yeah, there's so many different types of black holes. So the idea of a black hole is really this infinite curvature in space because of the mass in a small enough volume to curve space and to have an escape velocity that exceeds the speed of light. But in theory, you can have a black hole of any mass. So there's stellar mass black holes that are formed when massive stars explode and the remnant that's left behind shrinks into a black hole. There's also supermassive black holes that are formed at the centers of galaxies, kind of along with the formation of the galaxy in the history of the universe. And they're both black holes, but they form in very, very different ways with very, very different masses.
All of this information on black holes, all this detailed information on black holes is rather new. What has happened in academia to have this explosion of information?
Yeah, a little bit of it's the movies, I think, which is really, really exciting. Animation of the black hole out of this movie seems straight out of Interstellar to me, but it's wonderful because Interstellar was really guided by science. And so it was computer simulations, and it was mapping the rays and figuring out how a black hole with an accretion disk around it. So that's the thing, is that like we don't get light from the black hole, but the idea is that there's material around the black hole that's falling in.
And that's an accretion disk?
Yes, so that's what an accretion disk is.
In Star Trek, the original series, gravitational slingshots are a method of time travel. We see that time travel slingshot again on the big screen in Star Trek VI. In real life, the gravity assist maneuver was first used in 1959 by the Soviet probe Luna 3 and by a variety of American probes, including the Mariner 10 and the 2 Voyager probes. So can we break that down? What is a real-life gravitational assist or slingshot?
So a gravitational assist is when a spacecraft kind of uses a planet or another massive object to increase its own velocity. So basically what it does is the spacecraft kind of sneaks up from behind the planet, whizzes past it, but also changes direction, and it essentially borrows some of the kinetic energy from the planet to speed up a lot. And so you want it, it's all velocity vectors if you want to do the math at home. So the planet comes up in the same direction, or the spacecraft comes up in the same direction that the planet is already moving, but then changes direction a little bit nearby. And so you might use a little bit of propellant or rocket fuel to change the spacecraft's direction, but then that gives it a much bigger boost in velocity in that new direction.
Is that something that could possibly happen on Earth with a rotating object, or is that something that's unique to space?
No, any massive object can do it. And so sometimes the spacecraft will actually be launched and then start to orbit the sun, but then come back to Earth and use Earth for a gravity assist even.
Oh. Wow. Yeah. Wow. Lost in Space, Interstellar, The Martian, Passengers are some of the fictions that use this gravitational slingshot always around a planet. In the episode we're discussing, we're introduced to the Pike maneuver, a gravitational slingshot around a black hole used as a means of escape. Is the Pike maneuver a death sentence? Can you use a black hole like that?
It's definitely a black hole is a mass in space. It's just a higher density one, higher curvature of space one, but in theory, yeah, it can work.
So this idea, I incorrectly then assumed that a black hole would suck everything into it.
Yeah, black holes actually don't suck. If the sun, for example, for some reason shrank into a black hole, it would be about, I think about 3 times the size of the Earth. So all of the sun's mass, about 3 times the size of the Earth, would make it a black hole. But the Earth would continue to orbit normally, because all we care about is the mass, not necessarily how dense that mass is. From our orbit out here, we would be fine, except for the loss of the sun's radiation. So that would be bad. But we would continue to orbit normally.
Dead but orbiting.
Yeah, cold but orbiting, yeah.
The opening montage of Strange New Worlds draws heavily on images emanating from NASA and the Hubble telescope. They have also impacted the designs of our guest's clothing line, Sartorialist. What is it about those images, and how do you integrate them into fashion?
I'm still honestly figuring out what it is about the images. It's something that I love. Like, I feel so lucky to be an astronomer and to have both the inspiring images that were taken by these telescopes from the space probes, going back to even the Voyager days, but also to have the public interested in these and to recognize these. I think sometimes we take it for granted that one of the first things we teach little kids is the names of the planets and the order of the planets, and Saturn has rings and things like that. And I also have to be really appreciative of the Hubble Space Telescope team for starting out in the 1990s to release some of these images, not just for the scientific research, but just for the pure beauty of them. It's very similar image processing in order to do that, but it's slightly different to have an eye to it for the colors and the composition and the orientation and things like that. But it was something that they started doing with the Hubble Space Telescope, and it's been amazing since then to have these in the public domain and available for reuse and now recognized around the world.
Do you think, though, that the images are making us more excited about the stars?
Oh, yes, absolutely. Because they're also beautiful. Like, when so much work goes into making these images, it is like our artwork almost. The Carina Nebula from the JWST is one of my favorite ones. And a lot of people have said that it's so awe-inspiring because it's composed like a landscape from like the Hudson Valley School or something like that, with the kind of the brown orange underneath and the blue on top to make it look like a scene, but it's out in space, light years away.
Inspired by that, how do you take those images and turn them into fashion?
Yeah, that's one of the fun things, is figuring out, okay, how do we make this something that is fun to wear and kind of, aesthetically pleasing and flattering and all the things that go into clothing design that doesn't just look like, random splatter. But I had somebody called it tie-dye for nerds once. And so I'm trying to take it and make it a little bit more like high fashion than that. Like, okay, how does something look cool and not just look like space nerd? Or a little bit of both, maybe. We like space nerd too, so a little bit of both.
Of course, there are no simple missions in Star Trek. And at about 10 minutes into episode 4, Mr. Spock discovers an optical distortion and informs Captain Pike that there is a ship hiding in the vacuum of space behind a hologram, which is something that is created by reflecting light off molecules of air. And it's all big fun, and I love the episode. But could you have a hologram in space? Don't you need something there?
You could actually have a hologram without anything there. So most holograms actually work. They need some kind of material to create that light or something for the light to reflect or scatter off of. But at the same time, light is affected by the curvature of space as well. And so you might not actually need anything to interfere with the light. You might just need some kind of mass there that would curve space. And we see this actually, and we use it. So this is something in the universe that's called gravitational lensing. And so if we look at something massive, but it could also be dark matter. And so that's the nice thing, is that dark matter doesn't interact with any kind of light whatsoever. And so if there's a cloud of dark matter, then that's going to distort space, and that's going to change the way that we see light from background objects, basically.
Go Star Trek. I love this episode, but there were all kinds of issues in time that I didn't understand. Time shifts?
One of the things that they do is that they try to hide at the event horizon of the black hole by hiding their motion. But what you could really do at a black hole is change your clock relative to another clock. So basically stop time close to the black hole. And this is something that comes from also what they said in the episode, which is a gravitational redshift, where light that's leaving from near the black hole, so it's not inside of the black hole, but light leaving from near the black hole is going to lose energy and be stretched to longer and longer wavelengths. And so if you think of those longer wavelengths as kind of ticking off time, then the time of the ship near the black hole, as observed by the distant ship, is going to go much more slowly. And so they won't be able to see what's actually happening with that ship at the event horizon.
So as an escape maneuver,
plausible, but still dicey. Yeah, you don't want to get too close to the event horizon.
Right.
Yeah, but in theory, it works with general relativity.
Very exciting. Emily, at this moment, you're my favorite astrophysicist, but we're out of time, and I hope you come back again sometime.
I'd love to. Thanks for having me.